Vegetation structure. When we describe a site, we often begin by describing what the vegetation looks like. We use terms such as open woodland or sagebrush steppe, mountain meadows, or tallgrass prairie. The terms that we use evoke images of what the vegetation looks like, as well as the species that are included. It provides information about the three-dimensional or spatial arrangement of the plants, and we refer to this three-dimensional arrangement of plants as vegetation structure. Now, vegetation structure is an important attribute for both wildlife and livestock management because it provides essential information about different qualities of wildlife habitat, especially wildlife cover. For example, we can get information about the amount of cover available for shelter, for nesting, or bedding, or for thermal regulation, or cover for concealment, such as hiding cover, or for hunting, or escape cover. Because animals interact with their environment and as they move through it, the arrangement of plants greatly influences how they respond to their environments and is information that is useful for management. Well, vegetation structure is the three-dimensional distribution of plant biomass, but how do we actually measure that? If we look at these two pictures here, they are both open woodlands, but they have very different arrangement of plant material. You can see in the image on the left, there's a shrub layer, but not much of an herbaceous component compared to the image on the right, where there's a lot of material in the herbaceous layer and not nearly as many shrubs. In order to describe the three-dimensional nature of vegetation, we need to describe both the horizontal cover and vertical cover. By horizontal cover, we're referring to cover on a horizontal plane, or that is viewed from above. And we've reviewed methods of measuring horizontal cover in the previous lesson on cover. Vertical cover refers to the layering or arrangement of plant material in a vertical plane. In order to measure vegetation structure, we often take multiple measurements and then combine that information. The types of measurements that are most often used to describe vegetation structure are canopy cover, gap intercept, vegetation height, and visual obstruction. And so we'll look at each one of these in turn. Now, canopy cover characterizes horizontal cover, and we've already reviewed this. We know that when we measure canopy cover and report it, we often are reporting total cover, but we don't have information about plant spacing. Line point intercept is one of the best methods to use when we are trying to describe vegetation structure because it is easily conducted with other methods that we will be looking at. Gap intercept also characterizes horizontal cover, but in this case we're able to get information about plant spacing or the arrangement of plants. With gap intercept we can report on either canopy gaps or basal gaps. If we look at this illustration here, we see a number of plants that are intersected by a transect, and these plants have canopy, the larger part, and then there's a darker part in each one which represents the base of the plants. We can measure either the canopy gaps or the distance along the transect between the canopy. This is very similar to the continuous line intercept method that we reviewed in the lesson on cover, except that it's in reverse. We're not measuring the length of the canopy, we're measuring the length of the intersection of the gaps between canopies. We can also measure basal gaps. The length of these basal gaps provides information about vegetation structure that is useful in certain situations. In most cases, canopy gap intercept information is used for vegetation structure, although basal gap information may be applicable for certain systems. In this lesson, we will be focusing on canopy gap intercept. So the way that we measure this is we have to decide where a gap starts and where it ends. In order to start a gap, in order to measure that gap, it has to have a minimum length of at least 20 centimeters. And we decide that a gap is broken, or we will end the measurement on a gap, if 50% of a 3 centimeter segment is broken by canopy. So let's take an example here. We see a gap that starts at 38 centimeters and ends at 77 centimeters for a total gap length of 39 centimeters. Now, you may have wondered why we didn't draw this gap out to this larger canopy here, and that's because of this rule. The 3 centimeter segment has been broken. More than 50% of a 3 centimeter segment includes canopy, and because of that, the gap does not extend beyond this point here. There is another candidate gap over here. We would start this at 140 centimeters and end it at 152, but because it is less than 20 centimeters, we would not consider that to be a gap. Now, instead of just totaling all of the gaps, we need to get information about gap sizes overall in order to be able to talk about the spatial distribution of plants. And so with gap intercept data, we analyze the data by summarizing the gaps into different gap size classes. Here we see a diagram showing a 10-meter transect that's intersecting 3 different hypothetical plant communities that have different spatial arrangements. We can see in transect A that the plants are clumped together with very large gaps in between. Transect B, the plants are a little bit more distributed and the gap sizes tend to be smaller, and in transect C we can see that the gap sizes are generally quite small. If we analyze this, we would report that 100% of the gaps in transect A were in the largest gap class, which is greater than 200 centimeters, and in transect C, 87% of the gaps were in the smallest size class for gaps 25 to 50 centimeters. This kind of information gives us important data to relate to vegetation structure. Now, vegetation height is the first type of measurement we're going to look at that characterizes vertical cover. When we are measuring vegetation height, we measure the height of both woody and herbaceous layers. Usually this is done using a height stick, as you see the observer using in the image here, and we take multiple measurements along a transect. The way this works is by envisioning an imaginary cylinder around the height stick that is 30 centimeters in diameter. And we can use a couple of tools to make sure that we maintain this cylinder. We can either use a disc, kind of like a frisbee, with a hole cut out that can move up and down the height stick, or we can use a ruler that is either 30 centimeters in length or 15 centimeters if we're going to be looking at the diameter. You can see here the observer is using a ruler that is 30 centimeters in length or 12 inches, and it is centered on the height stick. Now the way we take measurements is by observing the plants and the plant material that occurs inside this imaginary cylinder. In this case, remember, we're going to measure both woody plant and herbaceous plant height. And so we measure, for woody plants, we measure the height, the maximum height of woody plant material where it occurs inside this imaginary cylinder, and so that would be at 40 centimeters. Note that even though the plant has some parts that are taller than 40 centimeters outside of the cylinder, we only measure the part that occurs within the cylinder. For the herbaceous plants, there are two herbaceous plants that occur within the confines of the cylinder, and we would take the measurement on the grass plant at 19 centimeters because it is the tallest part of herbaceous material that occurs within that cylinder. We would record the species as well as the height for both the herbaceous and the woody plant. Note again that we don't measure the tallest part of the grass that occurs outside of that cylinder. And these measurements usually are taken multiple measurements along a transect, and we simply average the values of the height measurements for both the woody and the herbaceous component. Visual obstruction also characterizes vertical cover, but really what makes it different from height is that it measures the amount of concealment that is provided by vegetation. The measurements that we take depend on both the viewing height and distance. There are a number of different visual obstruction methods, but they all have the same principle, that the stick or pole or cover board is observed from a set distance, that's the viewing distance, and the observation is made from a set viewing height. And so the height on the apparatus is then recorded. As I mentioned, there have been many approaches to visual obstruction measurements. Robel and others reported on using a cover pole in 1970, and Nudes reported the cover board. With a cover board, we have, usually it's about 2 meters tall, made out of plywood, and it's quite a bit taller than it is wide. With these different types of equipment, they often may be marked in different widths of the segments, or they may be measured with different kinds of protocols, different viewing distances or viewing heights. It's important, if you're using a visual obstruction method, that you carefully describe and document the protocol that you're using for measurement so that we can maintain repeatability. What they have in common is that the pole or the boards all have contrasting segments or bands painted or marked on them. So you can see these are 50 centimeter segments here. These are 10 centimeter bands painted on this Robel pole, and here we see smaller bands on this pole in the image at the top. The way that this is done is we record which bands are obscured from view and then calculate the percent of visual obstruction on a pole or a board basis. So let's take a look at an example of just one protocol. This is a protocol that is described in the monitoring manual by Herrick et al. In this case, we're going to put a cover pole behind this shrub. This cover pole is constructed of, it includes 4 segments. Each segment includes 5 bands alternating in black and white, and then ending with a red band that helps with recording data and not getting confused as you're taking your measurements and recording the data. We can see that there are 13 of 20 bands that are not obstructed by the vegetation. If we were to look at how this would be written down, we see that the top segment includes the top 5 bands. None of them are obstructed, so they all get marked with zeros. In the next segment of 5 bands, 4 of them are obstructed, and so on. Now we can see, let's look at just a couple here. The definition for obstruction is that the band cannot be covered by more than 25% by plant material. And so for this little band here, number 15 in black and number 13 in black, even though they are obstructed by some vegetation, less than 25% of the band is obstructed, and so they are not marked as being visually obstructed. In band 8, which is this black band here, you can still see the band, but more than 25% of it is obstructed by vegetation, and so it gets marked as being obstructed. To look at how these data are then calculated and interpreted, we do it on a segment by segment basis. So for segment 1, 0 out of 5 bands were obstructed, so that's 0% obstruction. Segment 2 had 80% obstruction because 4 bands were obstructed. Segment 3 had 20%, and segment 4 had 40% obstruction. The total average visual obstruction for the pole was 35%. And normally these calculations are done on sample sizes of multiple observations of the poles. So in conclusion, we can use a variety of methods: line point intercept, gap intercept, vegetation height, and visual obstruction methods in order to describe the 3-dimensional arrangement of plants in plant communities.